Thank you for joining us today. We're pleased to have with us Dr. Emily Warmann. She's from Caltech. She received her Bachelor of Science and Master of Science degrees in Mechanical Engineering from MIT and earned her PhD in Mechanical Engineering from the California Institute of Technology. And after completing her studies there, she remained at Caltech as part of the technical staff on the Space Solar Power Program. Dr. Warmann's research interests include systems design approaches to photovoltaics and the spectral dependency of photovoltaic energy production. And these interests extend more broadly to the integration of renewable energy sources into the future energy landscape to achieve sustainability and resilience. So please join with me in welcoming Dr. Warmann.
Well, thank you all for coming. As the title of my talk says, I'm talking about solar power systems engineering from Earth to orbit. The image you see on this first slide is a prototype of one of the projects I've worked on. I'll talk about it more as we get farther on. But I would like to stop and acknowledge the various agencies that have funded the various portions of this work, because we cannot work without them, sadly. So to start, to give you an overview, I'd like to start with a discussion of what I mean by systems engineering and why I think that's a valuable approach for photovoltaics in particular. And then sort of develop that conceptual approach to photovoltaics through some examples of my own work, looking at how solar cells respond to the solar spectrum and how you can do some analysis of that, the quality of the light and how that impacts their performance, and then design for the quality of the light that the solar cells receive. Talk about the Space Solar Power Initiative at Caltech, that prototype I just showed you. And then finally, I'd like to end with sort of a perspective on the work I would like to start moving into, the possibility of integrating photovoltaics with agriculture, and try to convince you why I think there are systems engineering benefits to be had there, even though it might seem perhaps counterintuitive to put solar panels over growing plants. So with that, I'd like to start just by considering a solar cell. So a solar cell is conceptually simple, right? It's a device that absorbs light and outputs an electrical current and voltage, and that's very simple. No moving parts, which is a big win. But as you can see, this is a schematic of a silicon solar cell. It's one of the more efficient types of silicon solar cells that is in widespread industrial production right now. So this is a commercial design. And as you can see, conceptually simple though the solar cell might be, there's actually a lot of design and engineering that goes into this device. So the specific composition of this main slab of material, this slab of silicon that absorbs the light and converts that light into excited electrons. So what's the actual doping level? The doping and distribution of these contact pads is highly doping regions that allow that current to be collected by this large rear contact on the solar cell. In itself, that serves as a mirror that reflects light that might be transmitted through the cell back up into that absorber material. It prevents light from escaping so that it can be converted. You know, the thickness and the doping of these layers that create the diode that separates the current to pass through the solar cell. You can imagine there might be a lot of optimization going into the thickness and number and distribution of these grid fingers that collect the current so that you can minimize your series conduction losses, your resistive losses, while also minimizing the amount of light that's simply reflected off the front surface because it hits a metal conductor instead of an absorbing solar cell material. And finally, of course, there's this intriguing waffle texture, which is optimized to allow light into the cell, but then trap it from escaping if it were to bounce off the back mirror, for example. So a lot of work is put into this device, and it's all aimed at this goal of maximizing the conversion efficiency, maximizing the amount of electrical power that's extracted from the solar cell per unit of light power that's incident upon it. So you take this solar cell, and then you place it into a module in the real world. And as you can see, from this diagram, this is just an example of a module that's produced by DuPont. There are, again, a lot of components and simultaneously a lot of engineering that go into these modules. So you have encapsulant material, a polymer that has to protect the solar cells and keep the light, keep water away from them so they don't degrade over time. You have a nice glass sheet that lets the light in. That's actually optimized to reduce absorption in the blue portion of the spectrum. So they use special glass even. You have obviously frame components that mechanically hold everything together and have to be robust under all the environmental loads from wind or hail or other considerations, and of course your interface to the electrical system. So these are a lot of components that are optimized primarily from the perspective of cost. They take the solar cells from the manufacturers, they put them together, they try to have something that impedes their performance as minimally as possible and at the lowest cost basis possible. Generally speaking, these two groups don't talk to each other too much. They do talk to each other some, but they're not really feeding back between the two of them. Now, interestingly, fairly recently, there's been a nice development in the photovoltaics community, which is the development of bifacial photovoltaics. So these are solar cells that absorb light directly from the sun or from the sky, but they also take reflected light from the environment around them through the backside. So we remember what a solar cell converts light to electricity. Well, we don't necessarily care where that light comes from. There's more light coming up from the ground in addition to the sun. Let's take it in too. But it's interesting to think about the compromises to the design that are required by this approach. First of all, you have to compromise the light trapping in your solar cell. If you're just going to compare them under top-down illumination, the solar cells that go in these bifacial panels will be slightly less efficient because they are not confining the light within the material as strongly. And secondly, now you have to compromise on material cost as well, because you can no longer have an opaque backsheet on your module. You have to have something that's transparent as well, and those materials typically are more expensive. But you can get up to 20% more electricity over the course of the year in service, depending on the conditions. And that is what solar cells are really made to produce. Not necessarily power. We care about that too, but power over the course of the year, integrated, how much electricity are you producing? And interestingly, as I was waiting for the seminar to start, I saw in Green Tech Media they have an article announcing that one of the largest solar installers in Europe is now going entirely to bifacial photovoltaic modules because they have determined that it improves their cost basis, their production, their system overall is benefiting from this approach. So I think that this is a nice encapsulation of this, what I mean by a systems approach. We have multiple components, they work together, and then you have to take a very careful assessment of the setting in which your overall technology is going to be deployed. And by doing that, you can get benefits that are very worth pursuing. So let's take another step back and think about where a solar cell gets its current and voltage. So that's what we mean by electrical power, right? So this is a plot of one of the standard reference spectrums for photovoltaics. Photovoltaics are always designed for a reference spectrum and then compared under spectrum simulators, a solar simulator that reproduces this reference spectrum as close as possible. And that's nice because it allows you to compare two different products or two different technologies on an equal footing. So this is a spectrally resolved picture of what that reference spectrum looks like. So on the x-axis, we have the photon energy. That's the different distributions of energy of light that's coming to us. And I've put the comparison to the visible spectrum just to give you a point of reference. On the y-axis, this is the power density in the spectrum. So the solar cell gets its voltage by how the material interacts with the light. So a photon with 1 electron volt of energy can raise the potential of an electron by 1 volt. So a solar cell that absorbs 1 electron volt light will put out roughly 1 volt minus losses. So similarly for 2 electron volts, if you're absorbing light at 2 electron volts and higher, you're going to put out 2 volts minus. Now, the catch is that you cannot absorb any light below the band gap of your material, so if you want to put out a higher voltage, you're losing all that power in the spectrum. And the form of that compromise is that you're reducing the current you produce. So on the right here, this is the sort of the flux density of the solar spectrum as a function, or plotted versus photon energy. And so you can see that if you want to, even though there's a lot of power density in this portion of the higher energy photons, in this portion of the spectrum, when you come to the actual power output of your device, because the flux density is lower there, you're going to lose out in overall power conversion. So what does that optimization look like? What does that trade-off look like? This is the maximum theoretical efficiency of a single junction solar cell versus the absorption limit, the band gap of that material. And as you can see, there's this nice peak that optimizes the trade-off. The shape of this peak is determined by sort of the bumpiness of the spectrum, the absorption bands in the atmosphere. And it is perhaps not coincidental that silicon is actually very close to the optimum band gap for this to match this spectrum. So what are let's take a little closer look at this efficiency. What are the losses in a solar cell? So here's the spectrum. We're back to the power picture. So if you have a single junction solar cell, again, this is a slightly different band gap, but the picture is all the same. This is where the losses occur in this conversion. So let's take them one by one. The light blue portion of this spectrum, this is all light that passes directly through the solar cell. It cannot be absorbed by that material and converted to electricity. It's just lost to pure transmission. In dark blue, this is the actual power converted in the different portions of the spectrum. And then in sort of light red and orange, these are losses caused by, in red, those are thermalization losses caused by the difference in the energy of the photons and the band gap of the solar cell. So a photon that's more energetic than the band gap of the solar cell, all that energy difference is just still be lost to waste heat. And then you also have these entropic losses that are just a function of it's a loss per photon caused by non-idealities in the conversion. All right. So with a single junction solar cell, there's not much you can do to address these. You can just match your band gap to the solar spectrum as best you can, but then you sort of have to live with thermalization because the sun is not a laser, and you have to live with entropy because the second law is the harsh mistress. So the way people address this is by choosing multiple cells to absorb different sections of the spectrum and then connecting them electrically. So this is a very schematic picture of that. You have one junction that collects mostly the blue light. It allows all of those other lower energy, longer wavelength photons to pass directly through. They're sequentially absorbed by the junctions underneath. And as you can see, they're connected electrically in series. So now you are adding voltage from your individual subcells. So you can increase the voltage output a great deal, and you can get a much higher efficiency. And this is what the loss picture looks like for, say, a 4-junction device. Now you can see the losses to transmission are very low. There are still a lot of photons in this portion of the spectrum, but there's very little energy per photon. So losing them is not a big loss. Now your power conversion covers a much larger portion of the incident power. Your thermalization losses are much smaller, and your entropic losses are larger overall because you have more photons interacting with the material. But as a percentage, your efficiency is much higher. So this is the way you can get more energy out of the solar spectrum as best we know it right now. But there's a catch. This cell is connected, all of these subcells are connected electrically in series, which means that they all have to absorb the same number of photons. Otherwise, if one of the subcells is absorbing a smaller number of photons, it will limit the amount of current that the other cells can pass, and you will sort of artificially restrict or throttle the power output of your solar cell. It goes back to heat. So as I mentioned, solar cells are all designed under a reference spectrum and then tested under the reference spectrum. But the question then becomes, how representative is that reference spectrum? Is it a good representation of the real world? If you design it under that spectrum, are you going to get that performance out in the real world? Well, this is sort of what goes into that reference spectrum. It's a specified, the particular inputs are you have atmospheric conditions. You have a particular model of the U.S. atmosphere. I think it dates back to the 70s, possibly the 60s. You're assuming an air mass of 1.5. That's a path length through the atmosphere. So 1 would be pointing straight up, zenith angle of 0, and 1.5 is 10 a.m., depending on time of year. You have specified values of carbon dioxide at 370 ppm. We know that's already wildly out of date. It assumes you're at sea level, and it has a particular value for the aerosol optical depth, or the pollutant level, particle pollutant level. And so add it all together, you get 900 watts per square meter of cumulative irradiance. This is a model of the light that comes directly from the sun to the Earth's surface at sea level. So if you're talking about places that are good for solar power generation, like, say, Phoenix, Arizona, this spectrum is not necessarily a bad model when conditions look like this. You know, sunny, blue sky, not too much scattering. But if you've ever been to Phoenix in the summer, you know that it often actually looks more like this. And so suddenly, this is clearly a condition where you're going to have a lot more scattering of light as it passes through the atmosphere. Intuitively, you might expect that this will have some impact on the spectral composition of light. So what will that do to our solar cells? I was curious. So the approach of answering that question, I started by simulating a year's worth of spectra for Phoenix, Arizona. Tragically, it's very hard to get spectrally resolved irradiance data for any location that you want. Those are hard to get. So what I did was I used a multiple scattering and absorption model. This is a very convenient tool that's available from the National Renewable Energy Lab. And if you can collect enough atmospheric data and inputs for the different values, like sort of the aerosol optical depth and precipitable water, you can input these into the model. It will model the path length through the atmosphere and model the spectra. So doing that for every hour of the day, just as a quick test, I thought, well, let's integrate them and see how close they are to that 900 watts per square meter. And the answer is that kind of close, you know, for the middle of the day. But there's still actually a substantial amount of variation. You know, how close is close enough? I don't know. And for the morning, it's not very close at all, even in the middle, the summer months of the year. So it would be nice to get a better handle on what is that variation in the spectrum. So this is one potential way of considering it. This is the average photon energy of all of those spectra plotted relative to the cumulative irradiance of each spectra. So the average photon energy is just the energy of the medium photon. So if your average photon energy is high, you're going to have more blue photons, more high energy photons in the spectrum. If your average photon energy drops, clearly you're going to have more red photons relative to the blue. So you can imagine this might have implications for a solar cell that's trying to absorb different spectral components in different subcells. So I took a set of simulated, these are ideal solar cells. They have multiple subcells from 2 up to 20. And I considered two cases. One where all of the subcells are connected in series, and one where all of the subcells are connected electrically independently of each other. They're allowed to float and have their current vary. All of these ensembles, it's important to note, are optimized for the AM 1.5D reference spectrum. So how do they do in Phoenix over the course of the year, was the question. All right. This plot is a little complicated, so let's step through it slowly. In this small panel on the right, this is the efficiency of those different ensembles under the reference spectrum. So they're, fairly high. And they do the thing you would expect. More subcells is more efficiency. On top, we have the electrically independent ones. On the bottom, these are the series-connected ones. And I'm plotting sort of the efficiency averaged over all the spectra that fall into different irradiance ranges. So how do they do when there's a lot of light? How do they do when there's not so much light? I'm using irradiance level as a proxy for the spectral composition, essentially. So there's a couple things to notice. First, the electrically independent ones, their efficiency is actually very close to their design efficiency. So when you design your solar cells, if their subcells are electrically independent, your performance is actually going to be close to what you would design it to be over the course of the year on average, particularly when the light is very high. The performance is very consistent. 2 subcells is always worse than 3, which is always worse than 4, and so forth. 20 subcells is always the most efficient at every illumination level. That is not the case for the series-connected cells, which are in this bottom quadrant. So here, unless you're talking about 2, 3, or 4 subcells, now the design efficiency is actually fairly different from the efficiency at every irradiance level. And you see this strong roll-off behavior, which starts earlier and earlier the more subcells you have. And in fact, the 20 subcell ensemble is nowhere the most efficient one here. The best you can do is 16, and only when the sun is really, really high. So there is a clear spectral dependence to the performance of these series-connected ensembles, and it's correlated very strongly with the cumulative irradiance level, which is perhaps not a surprise given how strongly the photon energy, average photon energy, is correlated with the irradiance level. So this is nice. You can take this and find out what it means for annual energy production. Up here on top, I'm plotting the efficiency of these cells under under the reference spectrum. And on the bottom, this is the annual energy production under these years' worth of Phoenix spectra. With the electrically independent subcells, energy production rises with the number of subcells, just like the efficiency does. With the series-connected ones, you get up to 8, and it's all diminishing returns. It's like that's the peak of your diminishing returns. So you don't get any more energy once you add subcells past 8. You can also look at the time dependence of this. So this is over the 12 months of the year. On top, I'm plotting the ratio of the series versus the independent performance. So it's the penalty that you're paying for having electrically in series subcells. And you see that there's this interesting dip right around July and August. That corresponds to the monsoon season in Phoenix. So the humidity rises. That increases the amount of scattering and absorption in the atmosphere because humidity and aerosol pollution are sort of synergistic in terms of how they absorb light. But if you are a solar system installer, you're trying to consider what you want to install in Phoenix to meet your air conditioning load, it's valuable information to know that your performance is going to drop 5% or more below what your reference efficiency is right in the months when your air conditioning load might be highest. So this is sort of interesting information. But this is all a particular case for one particular location. And we don't really want to be designing solar cells for individual cities. Let's try to maximize our economies of scale, right? So I wondered, can we turn this into a tool that has a broader geographic applicability? Well, this plot suggests that there's a correlation between the spectrum and irradiance level. So I went to the National Solar Radiation Database and looked at the correlation between these atmospheric inputs and irradiance level to see if we could maybe generate spectra that represent the different irradiance levels from dawn till noon at different times of the year. And for these parameters, which are the driving variability of the spectrum in the model, you do see quite a bit of variability. So air mass varies strongly, particularly at the lower, is very strongly correlated, particularly at the lower range. But then aerosol optical depth and precipitable water are more strongly correlated in the higher power ranges, which is actually where you produce most of your energy over the course of the year. So I took these values, I put them into the multiple scattering and absorption model, and generated 20 spectra that represent the illumination conditions at different irradiance levels. So Now you can take your solar cell model, you can simulate it under these 20 spectra, and then if you want, you can extend it beyond a particular location simply by taking the relative frequency of these irradiance levels at different locations, and you have the two numbers you can multiply together. So you have the performance at each irradiance level, you have the number of hours per year you have at that irradiance level, and so it becomes a very simple problem. These data are easy to get, which is nice for people who want to design solar cells and not spend a lot of time tracking down what the aerosol optical depth over time was at your different locations. So once you have these, you can combine it with your performance versus irradiance, and then you can extend it, say, over the geographic United States. So this is a projection of the annualized efficiency, so kilowatt hours produced per year divided by total incident solar power integrated over the year for an ideal 3-junction, multi-junction solar cell. It's mapped over the United States. It's an ideal cell at 500 suns of concentration, and that's why those efficiency numbers are so high. But the spectral dependence that causes the variability across the map is something that would be essential or fundamental to any spectrum splitting cell that used those band gaps, whether it was ideal or not. So this is the kind of range of variability of performance that you would expect. It's not particularly surprising, and it does confirm why you have a lot of concentrating photovoltaics in the southwest and mountain west, but not in the southeast. But it does also point to things like, well, if you think there's enough light in Utah and Idaho, this would be actually a good technology to deploy there. More interestingly to me, I think you can use it as a tool in the design process. So in this slide, on the left, we have a table showing the band gaps of 3 different solar cells. There's the ideal 4-junction, multi-junction, as optimized for AM 1.5, the reference spectrum. And then you have candidate A and candidate B. Now, candidate A and candidate B have identical efficiency under the reference spectrum. They are indistinguishable if you're going to just talk about how their performance is under the design. And if you're talking about whether you'd rather build A or B, there's not a lot to choose from. You know, I would not have a strong preference based on the specific band gap values. A crystal growth person might have a stronger impulse. But once you project their performance across the United States, suddenly you have a very strong reason to prefer design A. Because it's not only everywhere more efficient, but its efficiency is much more consistent across the United States. And so this is now a tool that you can use to evaluate the broader economic potential of a design by considering the actual setting in which it's going to be used. So both of these designs are less efficient than the ideal, but often cell designers are not, they're already compromising around the ideal for crystal growth reasons. So this gives them another way to evaluate designs rather than just comparing them under the design spectrum. So this brings us back to sort of the optimization picture I presented to you initially. Again, we're optimizing for energy production. That's what we want out of our solar cells. So to do that properly, just like with bifacial PV, you have to actually consider the real setting in which this technology is deployed. And once you do that, it might change your opinion of what the behavior in your optimization of your device structure looks like. And so down here, I'm showing you a picture of a prototype we built. It was a full spectrum solar project, and you can see there are 7 subcells. They are electrically independent as they are physically isolated. This optic both splits the spectrum and then concentrates it in these light pipes. And it was very much informed by, if you're wanting to maximize performance over a broad area, if you have electrically independent subcells, this map will be almost uniform in color. It would have a very uniform efficiency range. And that might increase your appetite for some complexity in your design, although probably not up to this degree. So let's consider a place where the environmental conditions are very different, and the spectrum, fortunately, never changes. So my most recent work has been on the Caltech Space Solar Power Project. This is definitely a large vision project motivated by the idea of having terrestrial baseload power on Earth, terrestrial obviously, but from solar power panels deployed in space. So you collect your light in space, you beam it down to Earth, and because the sun's always up, or almost always up at geostationary or geosynchronous orbits, suddenly you can get a lot more use out of your solar panels. So in order to make this work from a technological perspective, in order to make it even possibly possible, you have to achieve a specific power in your design that's high enough to overcome the cost of launching all of this stuff into space. So if you want to launch eventually square kilometers worth of solar collector, they have to be very light. And so consequently, our performance targets are very aggressive, and we're looking at efficiencies, preferably around 30% or higher, area mass densities, 50 grams per square meter, perhaps more like 100 grams per square meter, and a specific power in the 3 or perhaps 1 to kilowatt per kilogram range. So 1 kilowatt per kilogram, that's a little aggressive. So so as you might imagine, this is a very broad project. There are a lot of different disciplines and a lot of different research groups associated with it. Sergio Pellegrino is doing the structural analysis, the spacecraft design, also the dynamics, how they deploy, how they track and point, how they fly throughout the year. Ali Hajimiri's group is doing the microwave transmission phased array antenna structure, how you do the timing and phase control, as well as how you do the actual conversion. And then I work for Harry Atwater. We are focusing on the photovoltaic collector portion. So this requires analysis of, in a concentrating system, we have solar cells, we have reflecting optics, we have to consider the radiation shielding of the cells, and my portion has been mostly on the thermal design as well as the overall systems analysis. So how do you get to 10 watts per gram for photovoltaics, all right? It's a very simple calculation, right? You have power divided by mass. So in space, you have a solar cell. It's only about 40 grams per square meter. Okay, that's not too bad. But the radiation protection that they require to stand up to the particle radiation bombardment from the sun is actually fairly substantial. They need a few hundred microns of cover glass, and that adds up to about 400 grams per square meter. So the power out is your efficiency times the sun. So if you have 440 grams per square meter, your efficiency is prohibitively high, or it would have to be prohibitively high. So our approach has been to use ultralight concentrators at a low single, I call this 1D, other people call it 2D, linear concentrators. And in this way, we replace the heavy radiation shielding with ultralight optics. But in order for this design to function, all of these components have to be performing as many functions as possible. So now you have these sort of half troughs. Light comes in, is concentrated on a cell that's located on the adjacent concentrator. So this now has to serve not only as a reflector, but it also has to conduct the heat to spread it out over a broad aperture. And then it's also the surfaces that radiate that heat out into space. And you can see it's integrated then with the RF components underneath, and we radiate microwaves mostly towards the ground. So what does the systems trade-off of the optimization space look like for that 1D concentrator? All right, this is a plot showing the mass versus concentration for the different components in the system. So in the dark black line, that's the mass of the cell versus concentration. It goes down very rapidly because as you increase concentration, you're just decreasing the area fraction occupied by the solar cells. There's this fixed dotted line at the bottom. We're sort of assuming the structural components are agnostic of the concentration level. And then here we have the mass of the concentration optics. And the thing that goes up with mass, this is the the thermal management. So as you increase the amount of concentration, you have now more heat concentrated in your cell area, and you need more material to conduct that heat away and spread it. And so consequently, that red curve of the specific power versus concentration has a maximum point. With these input assumptions, it's about at 12 or 15 suns and 12 watts per gram, or no, 6 watts per gram. So I glossed over a lot of things in this plot. And one of them is the key assumption of the size of the solar cell. So it's listed as 1 millimeter. And the reason for that is that the overall system design space turns out to be very dependent on that cell size parameter. So if you increase the size of your solar cell, even for a given concentration, if you go from 1 millimeter to 2 millimeters, you've now doubled the heat concentration for a given heat amount for a given concentration level, and you have to then double your conductor mass as well. And so what we've identified, miniaturizing our solar cells down to a width of 1 millimeter is one of the key, I guess, technological insights or parameters that governs the success of this design concept. Now, we could go smaller. This would go farther, but at some point, your part count becomes prohibitive, and you can only take mass out of your system to a certain degree, so we've settled on 1 millimeter wide cells as a happy medium, for some value of happy medium. So how do we control the cell temperature? We have sort of 3 knobs we can use to reduce the temperature and get heat out of our solar cell. We can conduct it away, but then once we've conducted it away from the cell, we have to radiate it to space, and we have basically 2 surfaces with which to do that. There's the mirror surface itself, and then there's the backside of the mirror. Now, the amount of heat, the radiative power you're going to get is going to be a function of the emissivity of those 2 surfaces. So this plot on the left is a little complicated again. The different sheets are for different thicknesses of aluminum, and the actual level is the temperature. This is for 10 suns of concentration. And then the x and y axis is on the ground are the mirror and back surface emissivity. And what you see is that it's much more sensitive to the emissivity of the mirror, this front surface that has perhaps the best view to space, than it is to the backside emissivity, because that has a less direct path to radiate to space. Perhaps not surprising. So if you can assume that you're using a material that's fairly black on the backside, you could imagine taking a cross section. And this gives you a picture of how the concentration interacts with the temperature. So assuming the backside emissivity is about 0.85, which is high but not unachievable, you can see that by increasing the front surface emissivity, it allows you to have a variety of different system benefits. Which ones you select might depend on what your overall goals are. So you could either go to higher concentration. So if you can get your emissivity up in the above 0.5, suddenly you can think about designs that are actually 20 suns. If you're happy with lower concentration, you could really decrease the amount of material in your system by decreasing the aluminum thickness. So the amount of conductor that you're using to extract heat from your solar cells. So that would be a mass benefit. Or you could also think about operating your system at a lower temperature, because your solar cells will be more efficient at a lower temperature. So what this points to is that if you had the ability to engineer the emissivity of your mirror surfaces, you would get a lot of system engineering benefits out of that. And so we identified this as sort of a technology development area that would be highly beneficial for the project. And so that's more or less what some of my colleagues went out and did. So this is a structured optical coating. It's a sandwich of, in this case, it's chrome, polymer, and a metal back reflector. But you could also do it with a transparent conducting oxide, a polymer, and a back reflector. And then you have an optically reflective, ultra-thin coating structure, which has an emissivity of, in this case, it's 0.8, 0.5. I said that was technically achievable. And for the optically reflective one, it's more like 0.4 to 0.6, depending on the other conditions. And if you notice, this mass per area is 4 to 10 grams per square meter. So that's something we could potentially afford even in the aggressive mass budget of this design. So to take it back once more to this systems optimization picture, we have this aggressive target. We want something that's cheap enough to actually launch and get it into space at a large scale. And so that drove our optical design to this concentration concept, which is, it's not necessarily completely novel for space applications, but it is definitely the path less traveled. How this objective is envisioned, that definitely drives, we want large areas, so we need structures that can be folded and deployed autonomously. It definitely governs how the microwave antenna is envisioned. And finally, it tells us where we need to develop new technologies that we can bring into our system to achieve even higher performance. So as I showed you before, we haven't, it's not purely a modeling exercise. We have actually been building and prototyping designs towards this. As you can see, this one has a specific power that's a factor of 3 at least too low, but we are making progress towards it. In this case, it's using carbon fiber reinforced polymer mirrors that are ultra thin. We're using standard triple junction solar cells from Spectral lab. We could get a little more efficiency out of that. And if we could just get our optical efficiency up to a higher value instead of 50%, we would be much better. So still a long way to go. So with that, I'd sort of like to bring it back down to earth and talk about more my future research direction, so my areas of interest as I look forward as a researcher. And to do that, I'd like to talk about what this map represents. It's the cumulative solar radiation, sort of the kilowatt hours per square meter per year for different locations across the United States. And when I started as a photovoltaics researcher, I would go to talks and people would put up a square like this and say, we just need to cover an area like this with solar and we will be able to meet all of the energy needs of the United States. And they would mean it to be very encouraging. But I always didn't like, I've sort of never liked this vision because I know that under that square, you have a lot of beautiful natural lands that have been preserved. You have a lot of also productive agriculture. And there are also a lot of people who probably have strong feelings about what you put on those lands. And so while I'm definitely deeply committed to the vision of having photovoltaics generate a large fraction of our total energy budget, I would hate for that to come at the expense of conservation or agriculture, because those are also highly valuable things that our society depends on and values. So looking forward, I'm interested in the question of how do we make photovoltaics a good neighbor? If we want it to be a large portion of our energy landscape, it's going to be a large portion of our physical landscape as well. And we know that it will interact with its environment. So in particular, we know that photovoltaics generate a lot of waste heat. Unfortunately, the silicon solar cells are only about 20% efficient in actual modules. So 20% leaves 80% of all that incident power. That's a lot of waste heat that they're going to transmit to their local environment. So you can see on the left, this is a thermal image. People are interested in thermography because it helps them find defects in solar panels, but it also just shows you how hot they get. In the middle, this is a plot from an analysis from Arizona State. They were looking at what the environment in a large photovoltaic array was, and they found that there's a heat island effect. So the ambient air temperature in regions inside this large array is warmer by a few degrees in the middle of the day than it is at comparable locations nearby. So that waste heat is being transmitted to the environment, and it's detectable as sensible heat. And finally, on the right, this is a representation of sort of the way that energy dissipated from the environment can reduce the utility of photovoltaics. People are often interested in integrating them directly with structures like buildings. And if they're transmitting that waste heat to the structure, it can offset some of the energy they benefit. If, for example, that building has to run more air conditioning because it has to make up for that waste heat. So in this case, what they find is that it substantially increases the energy payback time of the photovoltaic, which is a stronger, becomes a larger component of the overall life than the manufacturing cost. So this is something that we need to consider. So I asked myself, can we engineer good thermal behavior from a photovoltaic array? So taking just a very preliminary look at this question, I began with the traditional panel floating in space. I just took a very, very simple finite element analysis model using COMSOL because it's very easy to get up and running. And what I find is that, yeah, actually to a fairly large degree, you can increase, you can trade off between radiating heat to the sky or to space and locally transferring it to the environment through convection. Now, there's nothing surprising about conservation of energy, which is all that this is showing. But the interesting thing is the degree of slope on those lines, and it shows that you actually have a substantial potential to reduce that local convective heat transfer if you can get your panel emissivity up into these ranges that I know are possible, possibly with engineered materials. So this is, as I said, very preliminary work, so there's a lot of wide open space ahead. There are a lot of questions to be answered. We need to get a better model that has more fidelity with the variability of the environment, a broader range of convective conditions. I would like to connect the model up with the actual electricity output of the module itself, and eventually start looking at how the details of orientation, how panel mounting, height, array spacing, and so forth interact with the details of specific ground cover to change these different heat transfer pathways, or how heat is portioned out amongst these different heat transfer pathways. And specifically, this is motivated by an interest in the possibility of potentially integrating photovoltaics with the agricultural system more intimately. So there are a lot of reasons you might think this could be beneficial. So it turns out for photovoltaic systems, the land acquisition cost is actually a substantial amount of the total system cost. So you could decrease that by making the land more available. You could decrease your land preparation costs by increasing the supply of lands that are already cleared, leveled, accessible to large equipment, as agricultural lands tend to be. Your permitting is also a substantial fraction of photovoltaic development costs. And you could facilitate that by focusing more on lands that are already developed as opposed to coming out of conservation. And then, finally, an obvious but perhaps unknown benefit of unknown size is you're going to perhaps increase the revenue for your farm. So that is not something to sniff at. So, of course, there are necessarily drawbacks as well. You're going to increase the cost of the structure needed for the photovoltaic, because now you have to elevate your array high enough to allow access for farm operations. You're decreasing the flexibility of the land that it's installed on. Photovoltaics are designed to last for 25 to 30 years. That's their warranty, actually. So you wouldn't want to remove them before that because you'd be sacrificing some of their useful life term. And so you've decreased the flexibility. And then finally, perhaps obviously, you've decreased the amount of sun that the crops underneath are going to get, and you're going to be impacting the microclimate of the field itself. And intriguingly, there's enough evidence to suggest that there's not necessarily a drawback to either of those two things. So it's interesting to think about the possibility of tuning those interactions for overall systems benefits. So, for example, you might be able to get a water use efficiency benefit. So this is a very simple analysis. It's just showing the potential illumination profile for two different array designs. One in which you have long rows of panels that are oriented north and south, so they're horizontal, taking light directly from the sky. As you can see, you get this pattern of light and shadow. You'd have the shade patches moving across the field over the course of the day. So if you're at a spot under the panel or in between the panels, you're going to get periods of sun, periods of shadow. But they're evenly distributed. So if you imagine tilting your panel slightly to the west, say 30 degrees, or 20 degrees, I think this was, Now, suddenly, your periods of illumination are going to happen more in the morning, and your periods of shade are going to happen more in the afternoon. That's exactly when the temperatures are highest and when your vapor pressure deficit is highest. So if your plants have their stomata closed at that point in time, they're going to be losing less moisture to the atmosphere. So if this is enough light over the course of the day for them to grow, they'll conserve water more in the right side configuration. And there's some evidence to indicate that that's what happens. A second possible intriguing benefit would be the possibility of frost protection. So if you have panels in your field, now you're reducing the view factor from the ground to the sky. And in some situations, that might be enough to reduce the amount of radiative transfer from the ground to the sky under cold conditions and extend the growing season. So you can grow more frost-tender plants either earlier in the season or farther north. So to take it back to this system picture one more time, I think there's a lot of potential here. We have to start perhaps with a system that makes economic sense for not just overall, but it has to make economic sense for all of the participants in that system. And I put it as a cost optimization, but it also has to make social sense. So that's an additional degree of complexity. And how that plays out will be a function of what the specific benefits are and how we can integrate that into the existing landscape. But long term, it seems like there would be a lot of potential because you could potentially envision this as a platform for the electrification of agriculture, either through increased use of robotics that could access the electrical network you now have in your field, or through crop surveillance or other non-chemical pest suppression. And it is too early to tell what those benefits might be, but I would like to find out. And so with that, I'd like to ask if you have any questions.